In this video, we'll talk about transform methods in special functions. In previous videos or even playlists, I've made mention of transforms a lot. But what is the transform methods, especially in the context of special functions? As an overview, we know that transform methods convert difficult differential and integral equations into simpler algebraic equations. I remember doing the Fourier transform playlist and all of that. So there was Laplace too. The major transform methods are Fourier transform, Laplace transform, Mellin transform, Hankel transform, Green's functions, convolution theory, operational calculus, and so on. So the general procedure is you have an original problem, you apply the transform to convert the problem into an algebraic solution, and then you have the inverse transform to take it back to the final solution, which can be interpreted in the context of the original problem. So let's go ahead so this is more like snapshots of these transforms in the context of special functions. So we start with the Fourier transform. The definition, the Fourier transform of a function f of x is given as f of like omega equals integral from minus infinity to infinity for f of x e raised to minus I omega x dx, and the inverse Fourier transform is given as f of x equals 1 over 2 pi integral from minus infinity to infinity of big F of omega e raised by I omega x d omega. So the interpretation then, the Fourier transform decomposes a function into sinusoidal frequency components. So you have any function then reduced to sines and cosines like that. And they have applications in signal processing, heat conduction, wave equations, quantum mechanics, and of course, image processing. Then talking about important properties of the Fourier transform, we have linearity, which means that if you take the Fourier of a multiplied by f of x plus b multiplied by g of x, it is going to be the same thing as a multiplied by the Fourier of f of x plus b multiplied by the Fourier of g of x. So that is linearity. So it means that Fourier transform distributes over functions that are added together like that. Is it distributes per se? It operates linearly over them. I think that's a better way to put it. Then you have the differentiation property. So the Fourier of the derivative of df dx, the Fourier of df dx rather, is simply the same thing as I omega f of omega. So like that. And more generally, we can say that the Fourier of the nth derivative of the function f with respect to x is actually I omega raised power n f of the Fourier of omega. Then we have the convolution property, which talks about the fact that the Fourier of f convoluted with g is the same thing as the Fourier of omega multiplied by the g of omega. The Fourier of omega, yeah, the f of omega and the g of omega. And as an example, I'm going to find the Fourier transform of f of x equals e raised by minus ax squared, where a is greater than 0. So using the standard results, we see that f of omega is equal to integral of pi over a e raised by minus, so that square root rather of pi over a, that's multiplied by e raised by minus omega squared over 4a. Thus, a Gaussian transforms into another Gaussian. So we start with, this Gaussian expression coming to end up with another term that is Gaussian in nature. So we can, run the code for that. So you have e raised by minus x squared here. And we try to plot all of that from minus 10 to 10. And then you get a picture like this. So you have a peak frequency around this point, around 500 frequency. Then we can talk about solving the heat equation. So if you consider the heat equation, partial u partial t equals k partial squared u partial x squared. If you take the Fourier transform with respect to x, that gives partial u cap partial t, which is equal to minus k omega squared u cap. So this ordinary differential equation has solution, u cap of omega comma t equals u cap of omega comma 0 multiplied by e raised to minus k omega squared t. That's if you solve this differential equation. So if you apply the inverse Fourier transform, it yields the temperature distribution. So, and then we move on to Laplace transforms. Laplace transform. So the definition, the Laplace transform of f of t is f of s equals the Laplacian of f of t, which is equal to integral from 0 to infinity, e raised to minus st, f of t dt. And the inverse Laplace transform is f of t, which is L inverse, the Laplacian inverse of f of s here. So that way we take it back to the time domain. And then you have, I mean, to the original domain, so to speak. So Laplace transforms are particularly useful for solving initial value problems. That I have a playlist on Laplace transform in case you want to understand that in some depth. So we have common Laplace transforms now. So if you take the Laplace of 1, that is 1 over s. Take the Laplace of t, you have 1 over s squared. The Laplace of t raised power n is n factorial over s raised power n plus 1. The Laplace of e raised power at is 1 over s minus a. Then the Laplace of sine at is a over s squared plus a squared. The Laplace of cos at is s over s squared plus a squared. So we have some common Laplace transforms that way. Then we have the derivative property. We've seen, okay, yeah, for the case of Laplace, right? So you have the Laplacian of f prime of t. The Laplacian of the derivative of f is actually s multiplied by f of s minus f of 0. And then the Laplacian of the second derivative is s squared f of s minus sf of 0 minus f prime of 0. So this is very helpful when you solve differential equations. So you can actually break down the differential equations into algebra, solve, and then take it back to algebra later. So this converts differential equations into algebraic equations. And once you're done, you can then convert the algebra back to uh, you can, I mean, you can then easily solve the problem, right? So an example is what you have here. You want to solve y prime prime plus 3y prime plus 2y equals 0 with these initial conditions. Y of 0 is 1 and y prime of 0 is 0. So if you take Laplace transforms of y prime prime plus 3y prime plus 2y, so, for y prime prime now, this is what you have. You have s squared, f of s minus all of this. So so by the time you factorize all of that, you end up getting s squared plus 3s plus 2y of s, and that is equal to s plus 3 by the time you tidy all of that up. And then you have y of s to be s plus 3 over s plus 1 into s plus 2. And then you can then have partial fraction decomposition of this, which then becomes y of s equals 2 over s plus 1 minus 1 over s plus 2. Now, I'm not really breaking this down because I have a playlist on it, which you can actually easily refer to. And now that we've got this in this tidy form, then we can now get the original y of t by taking the inverse Laplace of all of this. And then we now get 2 e raised per minus t minus e raised per minus 2t. That's the solution to this original problem. Using Laplacian, we just do algebraic stuff for the most part and take the inverse. So so if you put that in SimPy, right? Um, Using symbols t and s, and here we have y equals s plus 3 over s plus 1, s plus 2, and the solution is inverse Laplace transform, like that. So if you run the solution, you get this neat stuff that corresponds with what we have. That's 2 e raised per minus t theta t minus e raised per minus 2t theta t. Now you may be wondering, we don't have anything like theta t here, but if you do the print solution like that, so it tells you that is like a Heaviside function, Heaviside of t. And I think Heaviside, I know there's something about Heaviside and Dirac solution, Dirac function or something like that. So, but interestingly, we can solve it in this closed form and have this analytical exact solution. Then we move on to Mellin transform. The Mellin transform is m of s, which is equal to integral from 0 to infinity x raised by s minus 1 f of x dx. It bears a bit of resemblance with the Laplace transform we just saw. For Laplace transform, it's e raised by minus st f of t dt. But for this one now, it is e raised power x raised by s minus 1 rather, multiplied by f of x dx. So it is especially useful for studying scaling properties, and it has applications in number theory, gamma function, zeta function, and fractal analysis, and of course, asymptotic methods. I did a video already on asymptotic methods. You want to check that out. So if you observe carefully, discover that Mellin transform, if by the very structure, it bears a kind of resemblance with gamma function. So if you consider that f of x, this f of x now is e raised power x. If f of x can be e raised power x, then you have that m of s is equal to integral from 0 to infinity x raised power s minus 1 e raised power minus x dx. By this alone, this is exactly the gamma function. That means that what if you take f of x to be e raised power minus x, then the Mellin transform automatically is equal to the gamma of s. Therefore, the Mellin transform naturally generates the gamma function. So a good example will be to find the Mellin transform of f of x equals x raised power a raised power minus x. Then that means that m of s is integral from 0 to infinity x raised power a plus s minus 1 e raised power minus x dx. So recognizing the gamma function, that tells us that this Mellin function right here is actually the gamma of a plus s, like that. And then we can do, so if you put it into SimPy, right, using symbols x, X, S, and A, and guaranteeing that all of these symbols are actually positive, then we can have to integrate x raised to power s minus 1, x raised to power a, then exponent e raised to power minus x, like that, from 0 to infinity. And if you print the result, what you get is gamma a plus s, gamma a plus s, like that. So we then have, of course, this is gamma a plus s, but if you want to have it tidy, so if you do print result to get gamma a plus s, but to get the symbol, you just have this gamma a plus s. So having taken care of that, we move on to the Hankel transform. So for problems with cylindrical symmetry, Fourier transforms are often replaced by Hankel transforms. So you have examples, you have cylindrical heat flow. So you have acoustic waves, electromagnetic propagation, you have diffraction. The Hankel transform uses Bessel functions. So by definition, the Hankel transform of order n is h sub n of k equals integral from 0 to infinity fr j sub n of k r multiplied by r dr, where j sub n is the Bessel function of the first kind, and then the inverse transform is f of r, which is integral from 0 to infinity h sub n of k, j sub n of k r, k dk. And then you have the example, let f of r be e raised to minus ar squared. Then h naught of k is equal to 1 over 2a e raised to minus k squared over 4a. And then the transform preserves the Gaussian structure. So, so if you do this using SciPy and all that, so if you set a to 1 and k to be 2, and you evaluate that function for j0, you have the Hankel transform to 0.183939720585721, like that. And then we'll move on to the Green's function. So the basic idea is this, that if you suppose that L of y is equal to f of x, where L is a linear differential operator, Green's functions g of x comma psi satisfies L of g, which is equal to delta of x minus psi, where delta of x minus psi is the Dirac delta function. So then we have the general solution of this in this form. Once g of x comma psi is known, then y of x can then be the integral of g of x comma psi multiplied by f of psi d psi. And then Green's functions represent the response of the system to a unit impulse. So by way of example, you have, if you solve y prime prime, if you want to solve y prime prime equals f of x, subject to y of 0 equals 0 and y of l equals 0, the Green's function simply tells us that g of x comma psi is a step function defined as x into l minus psi over l when x is less than psi, and psi into l minus x over l when x is greater than psi. Then y of x is equal to integral from 0 to l of g of x comma psi f of psi d psi. Then we go on to the convolution theory. Convolution theory, the convolution of two functions is f star f convoluted with g of t, which is equal to integral from 0 to t f of tau g of tau t minus tau d tau. And convolution measures how one function overlaps another shifted copy. So the convolution theorem then, for Fourier transforms, you have the Fourier of f convoluted with g is Fourier of uh like f of omega g of omega. Then for Laplace transforms, the Laplacian of the convolution of f and g is f of s g of s also in the sense of Laplace. So this theorem is one of the most important results in transform theory. So if you take this example that if you let f of t to be 1, if you let f of t be 1 and g of t is t, then f convoluted with g of t will be integral from 0 to t. So of course, following the formula, right, that will be so normally you should have f of tau. So since f of t is 1, so f of tau will also be 1. Then the other part is g of tau minus t. So and since g is t now, so that will just be t minus tau dt. So if you evaluate that, you see that the f convoluted with g of t will be t squared over t over 2 like that. And verification using Laplace transforms. F of s is 1 over s. G of s is 1 over s squared. Thus, f of s multiplied by g of s is 1 over s cubed. So multiply these two together. And the Laplace inverse of 1 over s cubed is simply t squared over 2 like that. And we can actually do that convolution thing here, using SciPy or signal, the particular function is convolved from the SciPy or signal module. Then we have operational calculus. So I think sometimes people call this D operator. So operational calculus treats differentiation as an algebraic operator. So if you define D to be d dx, then d squared y plus 3dy plus 2y is 0 can be written as d squared plus 3d plus 2. It's more like you're factorizing this y now. This is second derivative, this is first derivative, and this is no derivative. So you have d squared plus 3d plus 2 y equals 0. Then you can factorize. So if you factorize that, you get d squared plus 3d plus 2 can be factorized as d plus 1 into d plus 2. Therefore, d plus 1, d plus 2 multiplied by y is 0. So the characteristic roots will then be that d is minus 1 and d is minus 2. So once that is got, then you have y is c1 e raised per minus x plus c2 e raised per minus 2x. So then you have the inverse operators. So if you consider d minus a y to be f of x, formally y is 1 over d minus a multiplied by f of x in that case, so that this operator notation forms the foundation of Heaviside operational calculus and Laplace transform methods. So by way of example again, if you want to solve d minus 1y equals e raised power x, since e raised power x belongs to the kernel of d minus 1, resonance occurs. So if we assume that y equals x e raised power x, then that means that d minus 1 equals x e raised power x, and that is equal to e raised power x here. Therefore, y will have to be x e raised power x. So, yeah. In summary, then, uh, we have methods and their kernels. For Fourier, the kernel is the what is the expression you have that you are bringing another function into. So by kernel, we mean something like this. If you come for um okay, for convolution theory, the kernel will be okay, well, I mean that has its own expression. I think the idea of kernel is better explained with things like Fourier and Laplace, or even Hankel, right? So the kernel here will be this J sub n of K of R here for Hankel. But when you come for uh Mellin transform, for instance, the kernel is x raised power s minus 1 because f of x can be any function. Well, the kernel is like what holds it all together. Then coming to Laplace, the kernel is e raised power minus st. Then coming to Fourier, you have that you have this e raised power minus I omega x because f of x can actually be any function. So that's the idea of kernel. So it's like what holds the transform together, the core of it. So, yeah, talking about summary of transform methods, for Fourier, the kernel is e raised to minus I omega x. For Laplace, it is e raised by minus sx. For Mellin, it is x raised by s minus 1. For Hankel, it is j sub n of k of x, just like I pointed out just now. For Green's function, it is delta x minus epsilon minus psi. That is the Dirac delta function. Then for convolution, you have the integral kernel. For operational calculus, you have differential operators. So all transform methods seek to convert differential equations to algebraic equations, making difficult problems easier to solve. Then we have the conceptual flow chart. Differential, so you have differential equation, you have a transform making it into an algebraic equation. You solve, and then after solving, you use inverse transform to take it to the final solution where it can now be easily understood. Then we have our key points again. Fourier transform analyzes frequency content. Laplace transform solves initial value problems. Mellin transform studies scaling behavior. Hankel transform is suited for radial symmetry. Green's functions provide impulse response solutions. Convolution simplifies integral operations. Operational calculus treats derivatives algebraically. Together, these methods form the mathematical foundation of modern applied mathematics, physics, engineering, and special function theory. And then we go on to our practice problems. Um, as usual, I'm going to solve two of them. Uh, so here you see questions 1 to 4. Questions okay, 1 to 4 now complete. Questions 1 to 4 here. Then, so the first is saying compute the Fourier transform of f of x equals e raised by minus multiplied by absolute value of x and all that. Show that the Fourier transform of the cube f dx cube is I omega raised by 3 f of omega, like that. Then we have 5 to 8, like that. We have 9 to 12. We have 13 to 16. We have 16 to 20. Okay, yeah, 16 to 20. Oh, this is, let me go by this now. Okay, we've done 13 to 16, so 17 rather, 17 to 20. But then there's a bonus too. So you have challenge problems here where you want to use Fourier transforms to solve the wave equation, u sub tt equals c squared u sub xx. Now, I'll be solving two problems here. I'll be solving problems 8 and 20. So this is problem 8. So problem 8 requires us to solve y prime plus 3y equals sine t with initial condition y of 0 equals 0 using Laplace transforms. So instead of using some other methods, we're going to use Laplace transform to convert it to algebra and then solve and take it back to get the original. So here we're looking for y for sure. Then the other problem I'll be solving is problem 20, which is to use the convolution theorem to find the inverse Laplace of 1 over s into s squared plus 1. So let's go for that. Okay, so problem 8 is the first one. Problem 8. So solve y prime plus 3y equals sine t, where y of 0 is equal to 0 using Laplace transforms. So we have step 1. So in step 1, we take the Laplace transform, right? So let me just say solution. So using the idea that the Laplacian of y prime is equal to s y of s minus y of 0, and the fact that the Laplacian of sine t is equal to 1 over s squared plus 1. Okay, then we obtain s y of s. Don't forget, um, this is what we have, y prime plus 3y equals sine t. So the Laplace of y prime is sys minus y of 0. So that's going to replace this. Then we have 3y, that this y doesn't change. That will just be y of s. The Laplace of 3 is 3y, right? And then sine t is 1 over s squared. So then so with all that, we obtain that s y of s plus 3 y of s, 3y of s is equal to, okay, I guess I want to go step by step. Let me write the original equation so you can follow, so I don't jump. So we obtain for y prime plus 3y equals sine t, and then y of 0 equals 0. Normally, this is what we should have. We have the Laplacian of y prime plus 3 times the Laplacian of y, and then the Laplacian of sine t, like that. So for y prime, right, we know that is the Laplace of y prime is simply s y of s minus y of 0, like this. So on one hand, then here we have 3. Laplace of y will simply be y of s again. Okay, and then sine t, we have 1 over s squared plus 1. But we already know that y of 0 is 0, right? So this will go to 0. So we have s y of s plus 3y of s, 3y of s is equal to 1 over s squared plus 1. So we can then factorize y of s here. So that means we have s plus 3 multiplied by y of s, because you have y of s here, y of s here. So s plus 3 will be remaining. So s plus 3 multiplied by y of s is now 1 over s squared plus 1. So that we now have y of s equals 1 over s plus 3 into s squared plus 1. So we need to do partial fraction decomposition. So to resolve y of s into partial fractions, so we know that um, we can let 1 over s plus 3 into s squared plus 1 be, this is linear, so we just have a over s plus 3. This is non-linear of order 2, so we have to start with bs plus c. So something of order 1 will be on top of it, all over s squared plus 1. So here we can then multiply through by the LCM. So multiply through by the LCM. That's the lowest common multiple. So, of course, that's clearly s plus 3 into s squared plus 1. So on the left-hand side, we have 1, and that is a. So s plus 3 cancels s plus 3. So we have a into s squared plus 1. Then on the other side, we have bs plus c into s squared cancels s squared plus s squared plus 1 cancels s squared plus 1. So we have s plus 3. So with that in place now, I like to use the cover-up method a lot. So for the cover-up method, we know that if we can set s to be minus 3, so all of this can be gone, all these things can go, and then we can move on. So I'm going to do that. I can just say set s to be minus 3, together just s plus 3 equals 0. So that means s is minus 3. So set s equals minus 3. That means you have, on the left, you have 1, then a into, now s is minus 3. So we have minus 3 squared plus 1, then plus bs, right? So you have b into minus 3 plus c into s is minus 3. That's minus 3 plus 3. So minus 3 plus 3 is 0. So that means this whole thing goes to 0. So we have 1 to be a into minus 3 squared is 9 plus 1. So that we have 1 to be, so 1 is equal to 10a. So that simply means that a is equal to 1 over 10. So we get a that easily. So now we have got a, so we need b and c to go. So how do we get them? So we can still use the cover-up method. So now there's no other number we can use to get zero out of it. But then we can just use small numbers that you can easily handle. So for the sake of seeing what's happening, I can just write this out. So we've got A already. So I'll just write out the expression again. So we have 1 into A s squared plus 1 plus bs plus c into s plus 3, I believe that is what we have. Yeah. So now we don't have anything to get 0 to eliminate anything. So you can just use any number you like, but as small as possible. So there you can say let s be, you can even let s be 0, you can let s be 0. So if you let s be 0, that means you have 1 equals a into 0 squared plus 1 plus b into 0 plus c into 0 plus 3. Now s is 0, right? So you have 1 equals a into 0 squared plus 1, that's a plus 1, a multiplied by 1, then b times 0 is 0. So you just have c here, 0 plus 3, that's 3. So 1 is equal to a plus 3c. But then thankfully we already know a to be 1 over 10. So but a is 1 over 10. So since a is 1 over 10, so you can come here and say a 1 is 1 over 10 plus 3c. So now we can easily get c. You can multiply 3 by 10. So we have 10 equals 1 plus 30c. So that 10 minus 1 is equal to 30c. Okay. So if that is the case, we then have 9 equals 30c. So c is 9 over 30. So if you divide through, 3 goes in 9, 3 times, 3 goes in 30, 10 times. So c is 3 over 10. So we have that. So now we have a to be 1 over 10. C is also 3. C is 3 over 10. Now we need to get b, right? To get b, so we've taken s to be minus 3, which eliminated one term. Now we've taken s to be 0, and with the help of a, we have got c. So we can also do another one. So you can just say, okay, let me write again. Again, we have 1 equals a into s squared plus 1, a into s squared plus 1 plus bs plus c into s plus 3. So again, I say let s be equal to minus, oh, no, not minus. I can just say 1 because we've used 0 and 1. So let s be 1. So we just have 1 now equals 1 equals a into 1 squared plus 1 plus b into 1 plus c into 1 plus 3. So that's 1 equals a. 1 squared is 1 plus 1, that's 2. So that's a into 2 plus b into, okay, plus b times 1, b plus c. 1 plus 3 is 4. Okay, so we have 1 to be 2a. 2a, 1 is equal to 2a plus 4b plus 4c. But remember that we already have a and c. But a is 1 over 10, c is 3 over 10. So that can help us to get b. So 1 is equal to 2 into 1 over 10 plus 4b plus 4 into 3 over 10. So with that in place, then it means that we have 1 equals 2 over 10 plus 4b plus 12 over 10. So there's no point trying to reduce to the lowest term because we can easily multiply 2 by 10. So we have 10 to be 2 plus 40b plus 12. So that means we have 10 minus 2 minus 12 equals 40b. So 10 minus 2 is 8. 8 minus 12 is minus 4. So minus 4 equals 40b. That means that b on its own is minus 4 over 40, which can then be reduced to the lowest term. So that's b equals minus 1 over 10, like this. So with all of that in place now, we can then go back to the original partial differential equation setup we have. this now. So now we have got A, we have got B, we have got C. So we can then put everything together. So we can say hence that our y of s, right? Now our y of s, we said it should be a over s plus 3 plus bs plus c over s squared plus 1. So, and we know that a is 1 over 10, b is minus 1 over 10, and c is 3 over 10. So we can just fix all of that up. So we have y of s equals 1 over 10 over s plus 3, then plus b, that's minus 1 over 10, minus 1 over 10 s plus 3 over 10 all over s squared plus 1, like this, so that if we tidy all of this up, we have y of s equals 1 over 10 into s. Okay, or better still, I think it's better to isolate. So we have 1 over 10, 1 over 10 into 1 over s plus 3, then plus, okay, if we split this apart, right, we can then still have minus 1 over 10 into s over s squared plus 1 on that side, then the other one plus 3 over 10 into 1 over s squared plus 1. So we have this. So now we finally have y of s like that. But that's not the last thing, right? Because we are solving a differential equation, so we have to take it back to what it is originally. So then it means that to get y of t, you need to take the Laplace of each of this. So using inverse Laplace transforms, okay, we can then have y of t equals the 1 over 10 inverse Laplace of 1 over s plus 3, then minus 1 over 10 inverse Laplace of s over s squared plus 1, then plus 3 over 10 inverse Laplace of 1 over s squared plus 1. So with all of that in place, it means that y over t is now 1 over 10. So if you have 1 over s plus 3, the inverse Laplace is simply of that will be e raised by minus 3t, then minus 1 over 10. For s over s squared plus 1, that is simply cos t, Then the other one, 3 over 10, inverse Laplace of 1 over s squared plus 1, that will easily be sine t. So, and that gives us our final result. That is our final result. Y of t equals 1 over 10 e raised by minus 3t minus 1 over 10 cos t plus 3 over 10 sine t. With that done, then we go to problem 20, which is the second problem I promised to take care of. So let's see how that goes. Problem 20. So problem 20 now. Problem 20 says to use the convolution theorem, to find the inverse Laplacian of 1 over s into s squared plus 1. So using the convolution theorem. So in that case, I have we have to factor into simpler transforms, right? So to factor into simpler transforms, we can write this, that we have 1 over s into s squared plus 1. That's the same thing as 1 over s times 1 over s squared plus 1. So in that case, we recognize that we recognize that the Laplace inverse of 1 over s is simply 1, while the Laplace inverse of 1 over s squared plus 1 is sine t. Okay, it is sine t. sine t. So if we let f of t be equal to 1 and g of t is equal to sine t based on our recognitions, right? So applying the convolution method, so we know that the convolution theorem, the convolution theorem states that the inverse Laplace of f of s, g of s is simply f convoluted with g of t, like that. Hence, we have Laplace inverse of 1 over s into s squared plus 1 equals integral from 0 to t f of tau g of t minus tau d tau. So substituting what we have the other time, right? Then tells us that Laplace inverse of 1 over s into s squared plus 1 is the same thing as integral, this is 0 to t, right? Integral from 0 to t, f of tau, f of t is 1. So f of tau will simply be 1 also. So we have 1. Then g of tau is sine t. So that means we have sine sine t minus tau d tau, like that. So that's what we have now. So this can be easily tidied up to 0 from t integral sine t minus tau d tau. So we need to evaluate the integral. So evaluating the integral, okay, we can let u be t minus tau. That's substitution. And then that means du dt is equal to 1. Du dt. Oh, du d tau, yeah. We are dealing with tau. Du d tau will have to be minus 1 because t is constant here. So tau is the factor. So that means that du is equal to minus d tau. Okay? Du is minus d tau. So the limit also, the limits become, look at the limits we are dealing with now. 0 to t. But now we are moving into the tau domain. So for 0 to t now, so since we let u be t minus tau, so we have u to be t minus tau. So for the lower limits, when we're still dealing with when tau is 0, right? When tau is 0, so we have u, okay, let's say at tau equals 0. So we have u equals t minus 0, which implies that u is equal to t. So we have that fixed. On the other hand, at tau equals t, tau is 0 and t are the limits. So at tau equals t, so it means that u is equal to t minus t, which is 0. That implies that u is equal to 0, like this. So we have a reversal. So with that in place, then, so we have u is t and u is 0. Therefore, we can say that the integral from 0 to t of sine t minus tau d tau is the same thing as integral from 0 to t of sine u du. Sine u du, because t minus tau is already u, and then the tau is minus. Okay, I guess I need to go step by step so you can really get the gist. So again, this should be integral from, we're now in the u domain now. So u at t tau equals 0, right? This is now t to 0 normally, right? T to 0. Then we have sine t minus tau, that is u dot the tau. Now for the tau, look at what's happening here. So du is minus the tau. That means the tau itself will have to be minus du. Okay, so now that we're in the u domain, so that's minus du. Okay, so in this case now we have minus integral from 0 to, okay, minus integral from t to 0 sine u du. The minus is out, but there's a rule that minus integral t to the minus sign can reverse the limits. So if we take away the minus, we can then have integral from 0 to t of sine u du. So that's the beautiful thing happening there. So, and with this now, we can then, if we integrate sine u with respect to du, so if you differentiate sine, you get cos. If you differentiate cos, you get minus sine. That means if you integrate sine u, you get minus cos u. So this is minus cos u when you integrate from 0 to t, like this. So that means we have minus cos. So we can even take the minus outside. So that's minus cos u from 0 to t. So then we have minus cos t minus cos t minus cos 0. Okay. So that means we have minus cos t. Cos 0 is 1, like this. So if we open that up, that means you simply have minus cos t. So that whole integral is minus cos t. So we can verify, right? We can then verify. So verify. So verify that taking, so if we take the Laplace transform, we take the Laplace transform, we have Laplace transform of 1 minus cos t. So that is simply Laplace of 1 minus Laplace of cos t. And you know that is Laplace of 1 is 1 over s. Laplace of cos t is s over s squared plus 1. So we can take the LCM. So that's s into s squared plus 1. So s goes here. You have s squared plus 1. 1 multiplies that minus s multiplies s. So we then have s squared plus 1 minus s squared all over s into s squared plus 1. So this cancels out. So we have 1 over s into s squared plus 1. So that makes sense that the Laplace of 1 minus cos t is 1 over s into s squared plus 1, which we actually, which the whole problem was all about, right? We want to use the convolution theorem to find the inverse Laplace of 1 over s into s squared plus 1. So the verification shows it's actually correct. So we can then conclude with the final answer. So we'll say, yeah, so the result is correct, right? As you can see. So we can finalize that the Laplace inverse of 1 over s into s squared plus 1 is equal to 1 minus cos t. And that is where it ends. So with this, we come to the end of this interesting video about transform methods in special functions. So again, look at the problems and tackle them based on what you understand. So here, 1 to 3 are showing clearly. Then we have 4 to 7. Okay, maybe we can see 4 to 6 completely. So 7 to 9, yeah, 7 to 9. Then we have 10 to 12, 10 to 12. Then we can see 13 to 14. I mean 13 to 16, 13 to 16. Then we have 17 to 8, 17 and 18. And finally 19, 19 and 20, 19 and 20, which I just did now. Then lastly, we have some challenge problems you can deal with. So with this, we come to the end of this interesting video. Let me know how helpful this is for you. If there's something else you'd like me to do, feel free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. If you have not subscribed, why not go ahead and subscribe right away? Uh, and of course, hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of the channel by clicking on join. That gives you some special privileges, that you'll find out when you click on join. ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.